All right, there we go. Okay, so this starts with chapter 9. What we did there, we basically did that Q equals VA, and then we did it, with a system that has changing pipe diameters. Okay. And then chapter 10 is Bernoulli's equation. So we got elevation head, pressure head, velocity head, head loss, and then using the chart. We also have hydraulic grade line on that. Okay. And then we had head loss theory. Okay. What does and does not cause head loss. So I think there's even a little question on top of that, those review questions that relates to that a little bit, isn't there? Higher pressure, rougher pipe, that kind of thing, do those cause or head loss or not? Okay, now laminar and turbulent flow, I just should expect you to know what those words mean, okay? Reynolds number, what do we do with that? Okay, Reynolds number tells you whether flow is laminar or turbulent. So that's what I expect you to know about that. I won't have you do any calculations with that or with the Darcy-Weisbach method, okay? That was that kind of complicated method we did early on. Right. So, I won't get you any of those to be doing, at least not calculation-wise, okay? Well, I wouldn't even have you do that with numbers. Just all that stuff, above Darcy-Weisbach there. Just know that kind of what I call conceptually. Just understand it enough to talk about it a little bit, or to write about it a little bit, I guess. So what I mean by that is this stuff. You should know what does and does not cause head loss. You should know the difference between laminar and turbulent flow, and you should know that the Reynolds number is used to figure that out. That's about it. Okay. Now, of course, I will have you do head loss calculations, but that'll be with the Hayes and Williams method, using the chart, okay? So you should be able to use the chart for C of 100 and C not 100. Should be able to do both, get that equivalent flow, and then be able to work through a Bernoulli's chart kind of problem where you find the head loss. Okay. So, that's kind of what's up with chapter 11. Chapter 12, minor losses, that's where you use those equivalent lengths. K factors we won't use those, so it's just equivalent lengths. And then if I do anything from chapter 13, it would be something pretty simple, kind of like the homework I gave you, where it just works out, kind of bang, bang, works out. Okay. All right. So that's the kind of stuff that could be on there. I can't get it all on there, I don't think, but I gave you some example problems here. We'll go over these in detail on Friday, I guess. But there's a little problem on where you just circle what would happen if the pressure goes up or the pipe gets rougher. What kind of head loss that would lead to. Here's a flow rate kind of problem. Notice these are numbers that are not on the chart, so you have to do the Q equals VA on that, okay? Here's a little Bernoulli's problem where you got to find the head loss. So you want to find the pressure at B, so you got to find the pressure right there. You're given all the other information. You're not given the head loss, you're given the flow and the pipe size and the C value and the distance. Okay. It's a minor loss problem. And then a little trickier Bernoulli's problem where you got to figure out what size pipe to use. Okay. So that's just some example problems. I could tell you for sure you'll definitely be doing the Bernoulli stuff where you'll find the head loss. I always get you one of those. I'll get you a minor loss problem for sure. That'll be on there. So, just kind of same sort of stuff we did with the homework, really.
This next Wednesday.
Monday, yeah. I'd do it Wednesday, but it's right before Thanksgiving, so probably won't do that. Yeah, we will, yeah. And I'll record it too, so. Yeah. All right. I'm going to go over these on Friday, probably be what I would do, I think. So I don't know, any general questions on that stuff?
You could have a copy of all your answers up there with all your hard work on it. That would be a real study guide.
Well, once you do them, I'll just remind me. I don't care. No, I'll put it up there. It's no big deal. But the thing is, I want you to do it, not just watch me do it. That's the thing. I'll if I remember, I'll get that up Friday. Maybe do something like that. Yeah, it's always easier watching somebody else do it. I know that. All right, so that's kind of the deal for Monday. Let's see. Do you guys want to look at that homework that you were going to turn in, but you didn't? I mean, here's that first one, 12.2. You want to find the L over D values. Let's see. On this thing, what you want to do here is find 4-inch pipe is 0.333 feet. And then you want to find the L over D values for these different things. I think this is 64, this is 12, and this is 20, I think. Yeah. So what you do, you can convert all those into equivalent lengths and then add them up and get the total. So the total equivalent length for the fittings is 32. So what that does is it adds 32 extra feet of pipe to the 8 and the 26 that are already there. So when you add everything up, you get 66 feet of pipe. So running the water through that, through the outlet, through the elbow, and through the open gate valve, what that does is that creates the same head loss as 66 feet of pipe would. Okay. And then you got C equals 100 and 150 gallons per minute and 4-inch pipe. So what you would do then would be to go find the head loss. Yeah.
2.5.
Yeah, 2.5. Okay, thanks. So it's 2.57. Now that's feet per 100 feet, and then you get 66 feet of pipe, so that's 0.66 100-foot lengths. So you can multiply that out, you get about 1.7 feet of head loss. Okay. So when you're doing this stuff, just be sure you do all the steps. You got L over D. What you want is the equivalent length of each of the fittings. Then you got to add those up and find the head loss for that equivalent length, basically. So you got a few steps to go through on that. So we're doing all right with that? So that's how you do those. Now this thing, that the sum of the two equals 1600, so you just got to figure out how the flow splits. We got 8-inch pipe that's short and 6-inch pipe that's long. So a lot more flow is going to go through the 8-inch than will go through the 6-inch. So I would just guess, I don't know, but 1200 and 400 maybe, start with that. And then, you can go ahead and find what the head loss would be for each of those. So if we've got, what do we got here? So if we've got 1200 and 400, okay, then we got 8-inch pipe and 6-inch, and this is C100. Okay, for the 1200, it's 4.14. That's off the charts. And then we multiply that times 4.8 because there's 480 feet of pipe. So for that flow, that 1208-inch pipe, we get 4.14 feet per 100 feet. You multiply that by 4.8, we get 19.87. Okay. And then for 6-inch, for 400 gallons per minute, what I get out of that is 2.2. But that's a lot longer, of course. That's 17.64. It's 1,764 feet. And when I multiply that, I get 38.8. Okay. So those are pretty different. I've got more head loss in the 6-inch side than the 8-inch. They're pretty different. So that's going to push more flow towards the 8-inch side. So then I could try maybe 1,300 and 300 and just see what I get out of that. And I get 4.85 and 1.29. And then I got to multiply them by the 100-foot lengths. And when I do that, I get 23.28. And I get 19.8. No, I don't. I get something else. Hang on here. I'm doing it right. Okay, then I get 22.76. And those are pretty close. They both round out to 23. So, you just call it that if you want. So 1,300 gallons per minute on the 8-inch side and 300 gallons per minute on the 6-inch side. So, that'd be good enough. So we doing all right with that? Okay. So I'll just give you credit for that assignment, I guess. I'll just do it that way. Okay. Yeah.
Here on this worksheet, these are the penciled in numbers, so those are the answers?
Yeah.
Okay.
Yeah, so that handout I gave you, of review problems, yeah, I got the answers on there. They're just written in pencil. All right. Why don't we look at pumps here a little bit more, just for fun. So, so what we did on this example here, are there any questions before we jump into this? Okay, so we wanted to find what's called the TDH for this pumping system. So we're not finding it for the pump, we're finding it for the pumping system that will push the water through this piping, this piping at the flow rate that's specified there. So we're going to push 1,300 gallons per minute through this piping system. And so we want to find how much energy essentially that takes, which is the TDH, total dynamic head. So the first thing we do, we just figure out how high we gotta lift the water, and that's 36 feet. You know, it's pretty easy. We just subtract the elevations of the two reservoirs. And then what we want to do, we want to figure out how much head loss we're going to have. And that gets a little bit more involved. I want to find the head loss, or the equivalent length for each of the fittings. So we got a square elbow, 2 of them. We've got standard entrance, square elbow, let's see. Oh, okay, I've got 2 square elbows. Or 2 standard elbows, right? I keep changing this stuff around. So 2 standard elbows, 1 ordinary outlet, and 1 ordinary inlet. And then I find the equivalent lengths of those, add them all up, and I get 118.6. I've also got 186 feet of pipe. So what I've got in that system is the head loss through that will equal the same head loss that you'd have in 304.6 feet of pipe. So then I multiply the head loss per 100 for C100 8-inch pipe, and I get the head loss, and then I just add that to the lift, to the static, total static head there, the 36 feet. Okay. So that's the deal. You just add 2 things together. You figure out how high you got to lift the water, just physically, how many feet up. But then you got to find the head loss. And that involves taking the length of the pipe plus the equivalent length of the fittings, adding those together and finding the head loss for that total length. Okay. So that's how you do that. And this is a big step that you'll use when you find the, when you size a pump, you know, that you would want to use in this system. You'd find this TDH. That would be a big part of what you would do. So why don't you do that for this one here, if you can. The next page, we've got a pump in a different configuration. Why don't you find the TDH for that? Ought to be around 139 feet when you get it all figured out. Questions you don't want to know, or that's your neighbor? Your neighbor's pretty smart. So that's tough to answer.
What's that? Convert 8 inch by convert to feet. 667. Instead of or like. What I did was I took the diameter times the whatever standard elbow is 64 times diameter of the pipe in feet times 64. Yeah, 2 so times about 2. I mean, you do the same thing. Those little ones, but they add it all together. Okay. That's what I'm thinking. Do you mind going back to the slide before? Or I'm sorry, the one that we worked out, that one.
okay with this one? You gotta lift the water 125 feet. You got 172 feet of pipe. You wanna find that pipe diameter in feet. So 8 inches is 0.667 feet. Then you look at the fittings. Find the equivalent, or the L over D value for each one. 64, 28, and 30. Got two elbows, so 2 times 64 times 0.667, 28 times 0.667, and 30 times 0.667. What you get here when you multiply this stuff out are the equivalent lengths for each of those fittings. So this is telling you how much pipe would cause the same head loss as those fittings do. And then you add those up and get the total. That's the L equivalent, the equivalent length of all those fittings together. So, okay, so you got 124 feet of pipe is equivalent, causes equivalent head loss to all those fittings, plus you got 172 feet, so 124 feet for L equivalent, 172 of actual pipe. So you add them together, you get 296 feet. So that piping system that you see there has the same head loss as 296 feet of just straight pipe. So you can take that and just make it 2.96 100-foot lengths, multiply it by the head loss per 100 on the pipe, 4.85, and get 14.36 feet. And then that's head loss, okay, that's energy loss. You add that to how high you got to lift the water, which is 125. And you get 139.36. So the basic idea is you're finding the total energy you've got to apply to the water. And to do that, you take the lift plus the horsepower, or plus the head loss. So you do have to do a little bit of mathematics there to figure out the head loss. But really the basic idea there is you're just taking that head loss and adding it to just the static lift, how high you've got to lift the water. But that's the idea. All right. Got any questions on that bit? Let's see. I think this is 27th. So this is not this coming Monday with the test. It's the next Monday. Okay. So it's the Monday after Thanksgiving. 13, 15. Yeah, I think that's right there. Okay. All right, so I'll cover that review a little bit on Friday. Okay. And then I'll see you on Monday for sure. Okay.